This is Geometry Lesson 8.6. We're going to be looking at the Pythagorean Theorem. So hopefully this is familiar, something you studied a little bit in middle school and algebra, and we will just reinforce it here. So the Pythagorean Theorem, it's one of the most useful theorems in all of mathematics, can be proved using the area postulate. And again, we're not going to go too deep into all of that. But your Pythagorean Theorem basically comes down to the formula for every right triangle. You have a squared plus b squared equals c squared, where a and b are the legs. So when we have this 90-degree angle, a and b must be the legs. It doesn't matter which one you call a and which one you call b, but the two of those must be your a and b. And the hypotenuse is always c, and that's the most important part of this formula. Across from the 90, the longest side of a right triangle, called your hypotenuse, that is always going to be represented by c here in the Pythagorean theorem. Now, just a quick deep dive on how this was discovered. If you line up three squares, all right, and their endpoints are touching and they form this right triangle in between them, we know that a square has all equal sides. So in this one that's designated by letter A, all the sides are A. So all the sides in this smaller triangle here are B, and all the sides here in this bigger triangle are C. We know that to find the area of those squares, you do base times height, length times width, which in a square is the same side times the same side because they're all equal. So a times a is a squared. So the area of this one is a squared, the area of this one's b squared, and the area of this is c squared. And what was discovered is when you line them up like this where their endpoints touch and form this triangle, if you add these two areas together, a squared plus b squared, you always end up with an equal area to this other one, c squared, the largest of the squares. And so this creates this Pythagorean theorem that was discovered and helps us solve for the side lengths of any right triangle. All right, so we're just going to look at some basic ones here. In example number 1, make sure we remember how to set these up. So we have a squared plus b squared equals c squared. Again, this only works in right triangles. This does not work in all triangles, just right triangles. A and b must be the two legs which come out from your 90. And then c is always across from your 90. It's your longest side, it's your hypotenuse. Okay, so 4 and 3 have to be plugged in for a and b. Doesn't matter where you put them. You can put 4 for b, you can put 4 for a. Doesn't matter. The important part is that c always represents your longest side or your hypotenuse. So we have 4 squared plus 3 squared equals c squared. You're going to algebraically simplify this side. So 4 squared is 16, 3 squared is 9. You would combine those. That's 25. And the most common early mistake when people are working with this is they just say, okay, this side's 25. And if you look at the picture, it doesn't really make sense, right? This length of 4 is not that much shorter than this one, so 25 would not make sense. That's what this side is squared. C squared is 25. So some number times itself gives you 25. Just like we did 4 times 4 to get 16, 3 times 3 to get 9. Whatever C is times itself gets you 25. So with basic numbers like this, we should know that it's 5, but algebraically, what you're actually doing is taking the square root of both sides, and the square root is asking what number or what value times itself gives you that expression. So the square root of 25 is 5 because 5 times 5 is 25. The square root of c squared is c because c times c equals c squared. So the value times itself that gives you c squared is c. And now we've simplified both sides here, and we have our answer for C. So just a reminder on how you do this in your calculator if the number wasn't quite so easy. Your square root button is located right above x squared in blue. So you're going to hit second and then the x squared button. You'll see the square root function pop up on your screen. You would punch in whatever number you want, like 25, and just hit enter, and that will give you your square root. So remember, 5 squared is 25, so the square root of 25 is 5. They reverse each other. All right, so let's look at another one, real basic, and just make sure we understand it. I'll have you try this one real quick. Pause the video. and then see how you do. All right, so hopefully you've already tried this one. Very similar to the other one, I did not give you C. That's going to be your unknown. That's not always going to be the case, right? One of these might be the unknown and they give you C. But in this case, the legs are the values that are given to us coming from the 90. So it doesn't matter which one you put in which spot, but A and B are the 24 and the 7, and C is our unknown. 24 squared is 576. 7 squared is 49. You would combine those and you get 625. And that's not necessarily one that you will know right off the top of your head. So we're going to hit second to get to the square root, punch in 625, and our answer there is 25. So the way we show this algebraically is that we actually square root both sides of the equation. Just like we can subtract from both sides, we can multiply both sides. It maintains the equality. We can take the square root from both sides here. And so C equals 25. Oops. C equals 25. And that should make sense. This side's 24. It's just a little bit shorter than that one, so 25 makes sense. Always make sure that it looks right with the picture. It should not be too far off the other numbers. Okay, so the converse of the Pythagorean theorem is true. If you have a triangle and you're not sure if it's a right triangle, might look like it, or you're just given the side values, you don't have a picture. If a squared plus b squared equals c squared holds true, then that proves that it is a right triangle. So if given side lengths, you can figure out if you have a right triangle, and you can actually find out if you have an acute or an obtuse triangle as well. Now, when we plug numbers in, if we're given three numbers, like you can see below, we're going to be given three side lengths of a triangle. The C is always the largest of them. Okay, so that's how you figure out what to plug in for C. So if you plug all three numbers in and you simplify everything out, if you get the same value on both sides, like 100 equals 100, that proves that it's a right triangle. That will only happen for right triangles. But let's take a look. We can also tell if something is obtuse or if things are acute. So it says it's also true that if a squared plus b squared is not c squared, then a, b, and c cannot be the lengths of a right triangle. So it's either going to be an acute triangle where all of the angles are less than 90, or an obtuse triangle where one of the angles is more than 90. So it says, furthermore, if c squared is greater than a squared plus b squared, then the angle opposite the side length of C is obtuse. Okay, so if C is greater than a squared and b squared, if the longer side when you square it gives you a greater value than a squared plus b squared, that's obtuse. If you're a highlighter, you're going to want to highlight those two in the same color. And then if C squared is less than a squared plus b squared, the angle is acute. So let's take a look. Sometimes when that's written out in words, it's confusing, but when you see it actually run with the numbers, it makes a lot more sense. So example number 2 here says, determine whether each triangle with the given side lengths is right, acute, or obtuse. So we're plugging straight into a squared plus b squared equals c squared. You'll notice that I gave you these numbers here in order in terms of smallest to largest. And so the largest is always going to be our C. They could give you these, they could have listed this as 7, 4, and 5. You still have to put 7 in for C squared. You don't just grab them in the order that you see them and put them in for A, B, and C. C is the largest number when we're dealing with three sides of a triangle. Okay, so I'm just going to drop these right in. 4 squared plus 5 squared equals 7 squared. And we're going to test this and see if that comes out to be a true statement. So 4 squared is 16. 5 squared is 25. 7 squared is 49. Simplify the left side. This comes out to 41, which does not equal 49. So it is not a right triangle. And C, it's all about C. C squared turns out to be larger than a squared plus b squared. So when C is greater than, this is an obtuse triangle. So what that's going to look like is instead of a 90, right, we've got this angle here that is larger than 90 degrees. So you got 4, 5, and 7 like that. So the angle that's across from your C, across from it, Remember, the largest side of a triangle is always across from the largest angle. Okay, so we know that this angle out here is more than 90. It's obtuse. Okay, the next one. Let's drop these numbers in. 20 squared, 21 squared. I put 29 in for C because it's my largest number there. Already got these run. Let's just drop them in. You would do it in your calculator. Those are those numbers squared. Left side simplifies to 841, which does equal 841. So we know that these side lengths form a right triangle. So this would look like this. A 90 degree. Across from the 90 would be the C, so this is 29. And these two legs, you could put them in any order, but the shorter side would be 20 and the longer side would be 21. All right, and then of course I'm going to give you one so you can see what an acute looks like. So it's 11 squared plus 40 squared. 41 is the largest. It goes in for C. So we get 121, 1600, and this is 1681. When you combine these, we get 1721 equals 1681, which is not true. So when you see not true, you know it's a acute or obtuse. It's not a right triangle. And now C is less than A squared and B squared. So this is an acute triangle. So if we quickly want to sketch an acute triangle, you want to make sure all the angles are less than 90. And that one almost looks like it's 90, right? So sometimes it's kind of hard to draw an acute triangle. And then you can just put this. This appears to be the longest. Oh, maybe this one, because this looks like the largest angle. So I would put the 41 here, and it doesn't really matter. Okay, but all of these angles would be less than 90 if this is an acute triangle. All right, let's take a look at the back. Some examples now. Different ways they can ask this question besides giving you just your basic right triangle. So we have to use prior knowledge to answer these questions. So a rhombus, we need to know some special things about a rhombus and their diagonals. Okay, a rhombus's diagonals, their measurements, we know that they are bisected. We know they're not equal to each other because if you think about a rhombus, it's kind of like a square that's on a tilt. And remember, a diagonal goes from vertex to vertex across. So this diagonal is going to be a lot shorter than this one in a rhombus. These are closer together than these. Where in a square, it's the same distance. So when we kind of slide this over like that, remember this is a rhombus, so all the sides are equal. These diagonals are going to bisect each other. So when I draw the diagonals, this is going to equal this, and this is going to equal this. And the other thing I know about a rhombus is it falls underneath of a kite, which means that these hit at 90 degrees. So all of these angles are 90, which if you look a little closer, we have 4 triangles now, 4 little triangles, and every single one of them is a right triangle, which means if we have 2 of their sides, we can use a squared plus b squared equals c squared to find our missing lengths. So the rhombus has diagonals measuring 36 and 48. We'll call this one 36 since that appears to be the shorter one. And it's being bisected. So that 36 is getting cut into 2 equal pieces, which is 18. So this is 18 and this is 18. And then the other diagonal of 48 is being bisected. So 48 divided by 2 is 24. So I know that this is 24 and this is 24. So if I separate one of those triangles, one side is 18, the other side is 24. The outside here would be a C because it's across from your 90, and that would be the actual side of the rhombus. So they want me to find the perimeter and the area. Okay, let's start with area. Area of a parallelogram, which is what a rhombus is base times height. But I don't have a height that's given to me here. A height would have to go from one side across to the other and hit it at 90 degrees. Okay, I don't have that. But a rhombus is one of those special quadrilaterals where the diagonals hit at 90 degrees. And we studied in the last section that the area of any quadrilateral whose diagonals hit at 90 degrees can be solved as 1/2 times diagonal 1 times diagonal 2. So depending on the information that's given to you, you can solve for the area of a rhombus in different ways. If you're given the base and the height, you can just multiply base times height because it's a parallelogram. But if you're given the diagonals, you can multiply the diagonals and take half. All right, so we're just going to go ahead and solve for the area real quick. We don't have to actually use the Pythagorean theorem here to help us find this. We already have the diagonals. They are 36 and 48. So we have enough information to find the area. You're just going to multiply those and take half, and that comes out to 864, and this is centimeters squared. You multiplied centimeters times centimeters, and you got centimeters squared. So the area here in this problem has nothing to do with using the Pythagorean theorem. But if we want to find the perimeter of this shape, we have to add up all the sides. All four sides are going to be equal because it's a rhombus. Okay, so we need to find this missing one out here. And because we have a right triangle, we can use the Pythagorean theorem. The missing side, like we talked about here, is across from the 90. That's our hypotenuse. That's our C. So we're going to plug in 18 and 24 for A and B. We're going to solve for C. This comes out to, if you square this and square this together, you can do that all in your calculator at once. You can do 18 squared plus 24, nope, 48. Nope, 24. Covered it up. Let's start over. So if you want to square each one, you can get the number underneath of it. But if you kind of want to simplify all at once, you can do 18 squared plus 24 squared just in your calculator, and you'll get the fully simplified version of it, which would be the same as doing 18 squared, which is 324, 24 squared, 576. You could write those and then add those together, and you'll get the 900. So C squared equals 900. We need to take the square root to find out what C is by itself. So I'm going to do the square root of 900, and that is 30. Now that's not the perimeter. That's just C. That side length equals 30. And so if I'm going to find perimeter of this shape, it's 30 plus 30 plus 30 plus 30. You have four sides. They're all 30. And so you're going to add all those up. Of course, instead of adding it 4 times, you could just do 4 times 30. That's fine. And the perimeter is 120 centimeters. Notice I didn't write centimeters squared. That's for area because we multiplied centimeters times centimeters. And here we just added a bunch of lengths. This is a straight line distance, even though it's going around the shape, not completely in a straight line. You could flatten this out to a straight line with all the sides extended, and it's just centimeters, not centimeters squared. All right, example number 4. Let's find the area of triangle FHG. They gave you the information that you need over here. They've pulled this out instead of putting it into the picture. But these side lengths, so everywhere you see 2 markings, they're all 3, so we could spread that out here in the picture. Everywhere we see 2 markings, it's a 3, and everywhere we see 1 marking is a 2. So the sides of this square, I know it's a square, all the sides are equal, and I've got 90 degrees, are 5. Area of a triangle, 1/2 base times height. So 1/2, we're just looking at this little triangle. Look for your 90. The 2 sides that hit at 90 are your base and your height. So times 2 times 3, doesn't matter which one you call the base or the height. That's 6, take half, and it's 3. Okay, so the area of one of these is 3, which means the area of all of these is 3. Now find the area of FDCB. That's a square. Area of a square is side squared or base times height. The base and the height are going to be the same, 5 times 5, so that's the same as writing sides squared, which in this case is 5 times 5 or 5 squared, which is 25. Now find the area of GHLN. So this kind of sitting sideways, rotated what appears to be a square here on the inside. And I want to talk about two different ways that you could do this. If I've already got this information, I know the entire thing over here is 25. So if I shaded this entire square, it's 25. And I've got these other square triangles here that are 3 each. And so if I want to find the area of all of them together, I do 3 times 4. So the combination of all of these together is 12. And so if I take this 12, all of these 3's, away from the area of the whole square, I'm left with this on the inside. So if I do 25 minus 12, I get 13, and that's the area of GHLN. So I took the area of the full square and I minus the area of the triangles. That leaves me the area of this inside square. So that's one way you could do it. Another way you could do it is you could look at all these right triangles and say, hey, Pythagorean theorem, I can very easily find out this length in here. That's going to be C. I've got A and B. And that will be the same for all of these, right? Because all of these triangles have a 2 and a 3. The C will be the same. And then once I've got a side length here, they're all going to be the same. I can just multiply side times side and figure it out. So let's take a look at what that looks like. There's some algebra here I want to talk about. So depending on what's given to you, you might have to solve a different way. In this case, we can do it both ways. So the two sides of my triangle are 2 and 3. I'm going to plug all that in. And I'm going to get 13 for c squared. Now, the square root of 13 is not a whole number, right? 2 times 2 is not 13. 5 times 5 is not 13. And if I actually plug it in my calculator and take the square root of 13, I do not get a nice number. Okay, so I don't want you to call this 3.6 and move on, because that's rounding and you're not going to have an exact answer. And we want exact answers here that we can use. So we are actually going to just say that c equals the square root of 13, and we're just going to leave it like that. So this measurement, instead of writing is about 3.6, we're just going to call it the square root of 13. All of these side lengths are the square root of 13. And so if I was going to find the area, it's base times height. Well, it's square root of 13 times square root of 13. Now, let's think about, just for a second, if I had, I'm going to slide over here, the square root of 25 times the square root of 25. What does that equal? Well, I can find those where square root of 13 is not a nice number. Square root of 25 is 5. Square root of 25 is 5. And then I multiply 5 times 5 and I get 25. So this shows you that when you multiply a square root times itself, you just end up with the number that you see underneath of this. So the square root of 13 times the square root of 13 is just 13. And we already knew that was going to be the answer. We found it right here. And so this gives you another strategy and also exposes you to a little bit of this algebra that you probably haven't covered in a little bit with square roots. All right, so you are going to run into some problems where you've got some goofy square roots that you need to simplify. And so we're going to do a quick review on how you handle square roots, how you simplify them, how you multiply them, kind of like we just touched on here, because you will run into that in this section. So real quick, let's simplify some square roots. The first thing you need to know is if you have a bunch of things under here being multiplied, you can separate them into separate terms. Okay, so all of them are being multiplied underneath the square root. You can separate them and then take the square root separately. And if one of them does not simplify nicely, you can just leave it under the square root, and we'll see that here in a second. But the square root of 9 is 3, the square root of x squared is x, and the square root of y squared is y. And so simplifying the square root of 9x squared y squared is just 3xy. All right, we've got this one, which we can separate into square root of 7 times square root of m times square root of 7 times square root of n. We talked about up here, any square root times itself just becomes the whole number. So square root of 7 times square root of 7, remember you can multiply in any order. So I can go ahead and multiply those two together and just get the whole number 7. The square root goes away. And I can't take the square root of either one of these. Notice they're not squared. So you cannot just write m or n. That's only when it's squared. And so I'm just going to leave those underneath the square root, recombine them instead of writing them separately. The simplified version of this is a whole number 7 times the square root of mn. We just talked about any square root times itself is just the number, so this is 5. But what you can't do then is say, well, this is just 15, right? 5 times 5 is 25. Whoa, hold on, the answer was 5. 5 times 3 is 15, but I still have the square root of 15. Right? It doesn't just disappear. A lot of people will just write 15 as the answer there. This was actually the square root of 25, and the square root of 25 is 5. So you are multiplying them. That number stays underneath the square root. If you can then take the square root of that number, you do. This is just a special case that we can make the jump without showing the middle step. Any square root times itself is just the whole number. But then when you have separate numbers, all right, don't just write 15. It's the square root of 15. Now, we also want to be able to simplify square roots. Okay, so what that looks like is instead of a decimal, we can simplify it with sometimes pulling out a whole number and then also leaving a square root next to it. So square root of 40, the way we do this is we split them into products. So two things that can multiply to 40. Now you could do like 20 and 2, 10 and 4, right? 8 and 5. There's different combinations of things that you can multiply together to create this. But what you're trying to do is pull out a number that actually has a square root, like 4 or 9 or 16 or 25, because the square root of those, square root of 4 is 2, square root of 9 is 3, square root of 16 is 25. It's 25. Yeah, I'm getting ahead of myself. Is 4. Square root of 16 is 4. Square root of 25 is 5. Square root of 36 is 6. So I'm looking for one of those special numbers that multiplies into 40, which would be 4 in this case. 9, 16, 25, 30. They don't go into 40, but 4 does. So this becomes the square root of 4 times the square root of 10, right? 4 times 10 is 40. And this square root of 4 is 2. So I can simplify it to a whole number 2. Square root of 10 is not a nice number. And so I can simplify it right there. Okay, those two are equal to each other. I just want to prove it to you here for a second. So you have square root of 40 is that nasty number right there. And if I type in 2 square root of 10, notice I get the same number. Okay, these are equal to each other. It's just like simplifying a fraction. It's like saying 2 over 4 is the same as 1 over 2, right? They're equal to each other. One is a simplified version of the fraction, and this is how you simplify a square root. When you're doing high-level algebra, this is necessary to help you cancel things out and further simplify more complicated fractions. So let's quickly practice this right here. You're going to see this pop up every once in a while, so we want to make sure we know how to do this. What's a number that goes into 50 that has a nice square root? It's 5. So square root of, or I should say 25, becomes 5. 25 times what gets me 50? It's 2. The reason I chose 25 is because it has a nice square root. Square root of 25 is 5. Square root of 2, not a nice number, stay separate. Remember, you can always check your answers on these. Take the square root of 50, then punch in 5 square root of 2, and make sure you do get the same answer, and then you know that you're good. 60. Okay, you look over here. What goes into 60? And 4 is going to be what goes into it. So square root of 4, you could do 60 divided by 4 to get 15. Figure out what it is. 4 times 15 is 60. So this becomes 2 square root of 15. Now the last one, I'm going to split this into 9 and 8. There's other ways to do it, but I'm going to split it into 9 and 8. 9 times 8 is 72. I want to show you that sometimes you have to go more than one step. The square root of 9 is 3. Square root of 8 is not a nice number, but square root of 8 can be split into another number that does have a square root. So I have to keep going if there's something that fits into it. So 4 times 2 is 8, and the square root of 4 does have a nice answer of 2. So this was 9 times, right? So this is still going to have a times between all of it. So all three of these now have been fully simplified. Square root of 2 can't go any farther. it's 3 times 2 times square root of 2, you can combine those. And so you end up with 6 square root of 2. And again, you can plug that into your calculator and check and make sure it's equivalent, but it is. All right, last one. How does this show up? Why do I need to remember how to do this from algebra? Sometimes when you run the Pythagorean theorem, you're going to get a nasty answer that's not a perfect square root. And the book very often is going to ask you to leave the exact answer. Find the exact length. Don't round a decimal. Okay, you get some big nasty decimal, don't call it 3.6. You're going to leave the square root as your answer and simplify it if you can. So in this case, we have a right triangle. Each leg is 8 inches. And if those are the legs, the hypotenuse is c. So if I'm going to run a squared plus b squared equals c squared, I'm going to get 8 plus 8, those are the two legs, equals c squared. So 64 plus 64, which is 128. And when you go to take the square root of 128, it's the first thing you should try. You see that it's a nasty decimal. So you're not going to call this 11.3. That would be an approximate answer because you've rounded it. We're going to leave this as the square root of 128. But if I can simplify it, I need to simplify it. So I need to look for numbers that have square roots that fit into 128. Now you could start with numbers like 4 or 9. Try them. Divide 128 by 4, divide 128 by 9. See if it fits in. But very often, if you take the smallest ones, you're going to end up with a problem like this, where you actually have to go multiple steps because you didn't grind all the way down to the largest number. So we want to look for the greatest common factor, the biggest number that goes into 128. So try something like 16. Very often, if 4 goes into something, then 16 does as well. So try 16, and sure enough, it's 8. So 8 times 16 is 128. So I could have picked larger numbers. There actually is larger numbers. Let me just show you. Maybe it was 36, not 36. It's actually 64, right? 64 times 2 is 128. Square root of 64 is 8. So you would have 8 radical 2. But let's say I didn't see that. I started off with the square root of 128, and I just tried to divide by 16, right? So let's clear this out. Let's say I just said 128 divided by 16 is 8. And so I have square root of 16 times the square root of 8. I know the square root of 16 is 4. That's why I chose 16. But square root of 8 can also split. And it will give you square root of 4 times square root of 2. Square root of 4 is 2. Let's bring everything down. Square root of 2 does not simplify, and so 4 times 2 is 8, and my final answer is 8 radical 2. I should check it. Square root of 128 is that nasty decimal. 8 square root of 2 is that same decimal, so I know I have simplified this correctly, and it is equivalent.